All right, let's jump straight into this explainer. Today we're basically acting as molecular detectives. We're looking at electron ionization mass spectrometry, which is this incredible technique that literally shatters molecules using high-energy electrons so we can read their unique, resulting fingerprints. If you've ever stared at a mass spectrum and felt like you were just looking at a random, chaotic barcode, well, this is exactly for you. We're going to decode the underlying logic of how these molecules break apart, and we'll turn those jagged lines into a clear, totally readable story of chemical structure.
To make sense of all this chaos, we're going to build a sort of mental cheat sheet by categorizing our chemical suspects. We'll cover Section 1, the molecular fingerprint, Section 2, the dehydrators, Section 3, the cleavers, Section 4, the rearrangers, Section 5, the rule breakers, and finally, Section 6, twin signatures. Let's get right into it.
Starting with Section 1, the molecular fingerprint.
So before we interrogate our specific chemical classes, we really need to understand the fundamental ways these molecules break apart once they're inside the ionization chamber. The very first thing that happens is a collision with an electron, which forms a highly excited radical cation. The molecule is just buzzing with excess energy, and to shed that energy, it has to break chemical bonds. Now, high-energy electron bombardment mostly leads to two specific types of breaks. You've got radical site-initiated alpha cleavages and charged site-initiated inductive cleavages. An alpha cleavage breaks the bond that's exactly one atom away from the radical site, whereas an inductive cleavage happens when an electronegative heteroatom essentially pulls an electron pair right toward itself. Ultimately, these two fundamental processes are going to dictate the vast majority of the shattered pieces we eventually detect.
Now, all of this breaking apart isn't just random chaos. It's driven by a core piece of logic known as Stephenson's rule. Think of this kind of like Markovnikov's rule in organic synthesis. It's an absolute anchor for our understanding. Stephenson's rule simply tells us that the fragmentation leading to the most stable carbocation is always the one that's favored. So when a molecule gets to choose which radical piece to lose, it will almost always eject the largest alkyl radical, simply because doing that leaves behind the most stable positive charge.
Moving right along to Section 2, the dehydrators. This includes alcohols, phenols, and thiols.
Alcohols are pretty notorious in the mass spec world. Why? Well, they often have super weak or even completely absent molecular ion peaks. The reason is they are just incredibly eager to lose a water molecule and stabilize. Take a classic example like cyclohexanol. The molecular ion peak at 100 is barely even a blip. Instead of hanging around, the molecule rapidly ejects water, which steers the fragmentation down a highly specific pathway, complete with a really unique ring cleavage pattern. And that brings us to a massively important number for cyclohexanol, the specific mass-to-charge ratio of 82. This represents the bicyclic radical cation that forms the exact second cyclohexanol loses that water molecule. So, if you're analyzing your data, and you see a missing molecular ion but a really strong M-18 peak, landing you at exactly 82, you've got a highly identifiable signature. It's a dead giveaway that an alcohol is hiding in your sample.
But what about their close relatives? Well, phenols, thanks to their stable aromatic rings, actually hold together much better. They'll show a strong molecular ion peak before eventually losing carbon monoxide. Thiols, on the other hand, which are the sulfur analogs of alcohols, they mimic that dehydration process, but instead of water, they lose hydrogen sulfide. That leaves a very distinct M-34 footprint. Plus, sulfur has a heavy isotope, sulfur-34, which drops an incredibly helpful M+2 peak right next to your molecular ion.
Okay, Section 3, the cleavers, ethers, and sulfides.
Our cleavers feature aliphatic ethers and thioethers. Much like alcohols, aliphatic ethers typically show pretty weak molecular ion peaks, but the upside is they undergo very predictable, aggressive splits that actually make them a joy to identify. Ethers are going to aggressively undergo alpha cleavage to lose an alkyl radical, or they'll use inductive cleavage to just snap off an alkoxy group entirely. Sulfides follow a very similar playbook, but with a neat twist. Because sulfur is larger and more polarizable than oxygen, it actually stabilizes the radical cation much better. Because of that, thioethers give you stronger, way more reliable molecular ion peaks before they start cleaving.
Let's dive into Section 4, the rearrangers, carbonyl-containing compounds.
Carbonyls, so we're talking aldehydes, ketones, esters, and carboxylic acids. They share some common one-bond fragmentations, but they are absolutely famous in mass spectrometry for undergoing some serious atomic gymnastics. While alpha and inductive cleavages are everywhere across all carbonyls, there's a special condition you constantly have to watch for. If the carbon chain attached to the carbonyl has at least 3 carbons, meaning it has what we call a gamma hydrogen, we run into the highly predictable McLafferty rearrangement. The molecule literally folds back on itself in a 6-member transition state, transfers a hydrogen over to the oxygen, and then just snaps off an alkene. It's really elegant.
But of course, before rearranging, they often just break. And here, Stephenson's rule is back in full effect. If we look at a molecule like 2-butanone, it's got a methyl group on one side and an ethyl group on the other. True to the rule, it preferentially loses the larger ethyl group via alpha cleavage, and that forms an incredibly stable acylium ion.
Because of that preference, the resulting MZ43 peak becomes the dominant acylium ion signature. It's exactly what you'll constantly be looking for when trying to identify aliphatic methyl ketones. It completely dwarfs almost everything else in the spectrum because that carbon-oxygen triple bond structure it forms is just so energetically favorable.
Moving over to carboxylic acids, the McLafferty rearrangement really takes center stage. Let's say we have butyric acid. Because it has that required gamma hydrogen, the molecule undergoes that 6-membered ring transition state we just talked about. This produces a massive, unmistakable signature peak at exactly m/60. Literally, whenever you're analyzing an unknown and you see a towering spike at 60, a carboxylic acid with a chain of at least 4 carbons should jump straight to the top of your suspect list.
Next up, Section 5, the rule breakers, nitrogen compounds.
I like to call these the rule breakers of our molecular lineup because they stand out immediately, even before you look at the fragmentation patterns. You can literally spot them the second you calculate their overall mass. And this is all thanks to the nitrogen rule. Since nitrogen has an even atomic mass but interestingly forms an odd number of bonds, compounds containing an odd number of nitrogen atoms must have an odd-numbered molecular weight. It's a hard rule. So if your molecular ion has an odd mass, say 45 or 73, you instantly know you're likely dealing with a suspect harboring an odd number of nitrogens, like an amine, an amide, or a nitrile.
For instance, when you look at the spectrum for ethylamine, you'll notice an overwhelming peak from alpha cleavage that practically dominates the entire thing. The molecular ion is sitting right there at 45, which absolutely confirms that odd mass rule. But the molecule itself desperately wants to lose that methyl radical.
Once it drops that radical, it leaves behind an aminium ion. And honestly, you should absolutely lock these diagnostic numbers into your memory. Unbranched primary amines just scream their presence at m/Z30. Primary amides show up dependably at 44. And nitro compounds drop these highly characteristic 30 and 46 fragments as their nitro groups literally break apart into NO+ and NO2+ ions. Keep those numbers handy for sure.
Finally, Section 6, twin signatures, alkyl chlorides and alkyl bromides. If nitrogen compounds are the rule breakers, the halides are definitely the loudmouths. They offer the most visually dramatic and easily identifiable clues in all of mass spectrometry. If you check out the far right side of a spectrum for something like 2-chloroheptane, you'll see something cool. Because chlorine naturally exists as 2 isotopes in nature, chlorine-35 and chlorine-37, we see a highly distinct M and M+2 twin peak setup. And since chlorine-35 is roughly 3 times as abundant as chlorine-37, these twin peaks always appear in a precise 3-to-1 ratio. It looks exactly like a little staircase stepping down at the far end of your graph.
Bromine, on the other hand, leaves a completely different visual clue. Bromine's 2 naturally occurring isotopes, bromine-79 and bromine-81, exist in almost perfectly equal natural abundance. This creates a stunning 1-to-1 twin tower ratio for the molecular ions. I mean, you physically cannot miss it when you're looking at the data. It's incredibly obvious.
So, as a mass spec detective, your very first move should always be to instantly check the high mass end of your spectrum. A 3-to-1 step down means chlorine is firmly on the scene, while those perfectly matched twin towers mean bromine is your culprit. It is the ultimate, undeniable chemical fingerprint.
So, we've mapped out the fingerprints of the dehydrators, the cleavers, the rearrangers, the rule breakers, and those unmistakable twins. By understanding the actual organic chemistry logic driving these fragmentations, whether it's the stability of an acylium ion or the 1-to-1 natural abundance of bromine, you don't just have to blindly memorize peaks anymore. You now have a working mental field guide to decode any spectrum. The real question is, looking at your next set of lab results, which chemical suspect will you track down first?